somewhere between 50 and 120 meters beneath the Pacific Ocean, a heat reservoir so large it has no precedent in the observational record is quietly loading. Scientists call it the octane tank, and right now, that tank is full. Models that predicted a moderate El Niño in January have swung violently upward in just 8 weeks. But the Pacific is not doing this alone. Earth's magnetic shield is fracturing in ways satellites have never recorded before. The sun refused to calm down after its predicted peak, and the western United States just experienced 105-degree heat in March. Stay until the end. Because what these 4 systems are doing at the same time is the question almost no one is asking yet. If this has you hooked, subscribe to the Skylab, because the models are revising faster than the headlines can follow, and we'll be here every step of the way as this story develops. Drop a comment telling me where you're watching from, and be honest with me, do you think a subsurface heat reservoir with no precedent in recorded history, a fractured magnetic field, an overactive sun, and record March heat all arriving together is just bad timing, or is the Earth system trying to tell us something we are not quite ready to hear? Now let's get into it. Part 1. The reservoir no one expected. Something is hiding beneath the Pacific Ocean, and it has been hiding there quietly, patiently, for months. Not a creature, not a geological formation, something far more consequential than either. Scientists tracking the tropical Pacific have discovered a massive reservoir of warm water sitting between roughly 50 and 120 meters below the surface, stretching across the entire equatorial Pacific basin. It is enormous. It is unprecedented in the observational record, and almost nobody outside the climate science community is talking about it yet. Here is what makes this so unusual. When most people think about ocean warming, they picture the surface. They imagine satellite images of bright red patches spreading across a map, the kind of images that end up on the news. But the ocean is not a flat thing. It is a layered system, a stack of water masses sitting on top of each other, each with its own temperature, its own density, its own role in the climate engine. And right now, the most important action is not happening at the surface. It is happening below it. The warm water sitting between 50 and 120 meters depth is not visible to a casual glance at sea surface temperature maps. The surface may still appear relatively neutral. A person standing on a beach in Peru or in the Philippines would feel nothing unusual. The ocean would look the same, the waves would feel the same, but below, the system is loading. That is the word forecasters use. Loading. Like a spring being compressed, like a battery being charged. The energy is accumulating in a place where it cannot yet escape, waiting for the atmospheric conditions that will allow it to surge upward and outward into the climate system. Forecasters have a nickname for this subsurface heat reservoir. They call it the octane tank. Some call it the jet fuel of El Niño. The metaphor is accurate in a surprisingly literal way. Just as an engine cannot run without fuel stored somewhere accessible, an El Niño event cannot fully develop without a reservoir of warm subsurface water that can be brought to the surface. The bigger the reservoir, the more powerful the potential event. And right now, that reservoir is, by several measurements, larger than scientists have observed at this stage of development in the modern record. Let me explain why subsurface ocean heat matters so much more than surface temperature in the early stages of El Niño development. The ocean stores heat in layers because water of different temperatures has different densities. Warm water is less dense and tends to sit on top of cooler, denser water. The boundary between these layers is called the thermocline. When trade winds blow strongly across the equatorial Pacific, they push warm surface water westward, allowing cooler water to rise on the eastern side near South America. This is La Niña. But when those winds weaken, the warm water piled up in the western Pacific has nowhere to go but back east, and the thermocline tilts. Warm subsurface water begins migrating towards South America. This is the beginning of El Niño. The more heat stored below that thermocline, the more fuel is available for that migration. Now here is where the story gets genuinely alarming. Climate model projections have not been gradually inching upward, they have lurched. In January 2026, most models were projecting a moderate El Niño by mid-year. A fairly unremarkable event, something meteorologists might mention in a seasonal forecast and the general public might never notice. Then February arrived. Several major modelling ensembles increased their forecasts into strong El Niño territory, and then March came. Some model runs are now showing anomalies approaching what scientists classify as very strong, or even super El Niño levels, by fall 2026. For those unfamiliar with what super El Niño means in practical terms, the classification threshold for a super El Niño event is typically a sea surface temperature anomaly of around 2 degrees Celsius or more in the key monitoring region of the Central Pacific, known as the Niño 3.4 region. Some ensemble members are now showing anomalies approaching 2.5 degrees Celsius. That is not a moderate warming, that is a climate system releasing enormous amounts of stored energy into the atmosphere in a matter of months. What scientists use to arrive at these projections is something called ensemble forecasting. Rather than running a single simulation of how the climate system might evolve, modelling centres run dozens or hundreds of slightly different simulations, each starting from marginally different initial conditions. The spread of those simulations gives forecasters a sense of the range of possible outcomes, from the most optimistic to the most alarming. When many members of an ensemble converge on the same result, scientists take notice. When both the European and United States seasonal forecasting systems point in the same direction, that matters even more. Right now, multiple major modelling systems are showing a strong convergence toward significant El Niño development. Scientists are careful. They are professionally trained to be careful. No one is standing at a podium and declaring a catastrophic super El Niño on the way. The event must still navigate through what forecasters call the spring predictability barrier, which we will return to later. But the unusual speed of this escalation, happening at what are still considered long-lead times in seasonal forecasting, is drawing serious attention. For a sense of historical scale, consider the El Niño of 2015 to 2016. It was one of the strongest events in recorded history. It caused devastating floods across parts of South America, catastrophic droughts across Southeast Asia and Africa, and contributed to the hottest year ever recorded at that time. The early subsurface signature of that event looked alarming. The current subsurface signature looks comparable, and in some measurements it looks larger. The fuel appears to already be in the tank. The question that forecasters are asking quietly among themselves, the one that keeps them staring at model output at 2 a.m, is a simple one. Is the atmosphere about to strike a match? Part 2. The Pacific just flipped. Until recently, the Pacific Ocean was doing the opposite of what it is doing now. For the better part of the previous year, the tropical Pacific was locked in a La Niña pattern, the cold phase of the cycle that climate scientists call the El Niño Southern Oscillation, or ENSO. La Niña is in some ways the mirror image of El Niño. Trade winds blow harder than usual across the equatorial Pacific, pushing warm surface water westward into the Indo-Pacific region. Cold water wells up along the coast of South America. The western Pacific gets wetter. Large parts of South America, the southern United States and East Africa get drier. Global temperatures, while still elevated, get a slight downward nudge from the cooled Pacific. La Niña is not dramatic in the way that El Niño is dramatic. It does not generate the same global headlines. But it is doing something important the entire time it is operating. It is loading the system. Every month that strong trade winds push warm water westward, more heat accumulates in the western Pacific. More warm water piles up in the ocean. And when La Niña eventually collapses, all of that pent-up heat has to go somewhere. The La Niña event of 2025 to 2026 has now collapsed. The transition happened faster than many forecasters anticipated. The Pacific is moving through neutral conditions and the data suggests it is not stopping there. Here is what the numbers currently show. The Niño 1+2 region, which covers the waters closest to South America off the coast of Ecuador and northern Peru, is already running at approximately 1.26 degrees Celsius above average. That is not neutral, that is warm. The Niño 3 region, which spans a broader section of the eastern Pacific, is also warming. The Niño 3.4 region, which is the primary benchmark that scientists use to officially declare and classify El Niño events, is still close to neutral, but rising at a pace that has forecasters watching very carefully. The geography of which region warms first actually tells scientists something meaningful about what kind of El Niño is forming. When warming leads from the eastern Pacific, from the Niño 1+2 and Niño 3 regions near South America, scientists call it an east-based El Niño. When warming is concentrated in the central Pacific, they call it a Modoki event, after the Japanese word for something that resembles but is not quite the same thing. East-based events and Central Pacific events are not equally powerful or equally dangerous. East-based events, the kind that appears to be developing now, tend to be stronger. They tend to have larger global impacts. The three most catastrophic El Niño events in the modern record, 1982-83, 1997-98, and 2015-16, were all primarily east-based events. Consider for a moment what those three events looked like when they arrived. The 1982-83 El Niño killed an estimated 2,000 people, caused $15 billion in damages, triggered catastrophic floods across the western United States and Peru, and drove some of the worst droughts in Australian and South Asian history. The 1997-98 event was even stronger. It produced record rainfall across East Africa, devastating droughts across Indonesia and Australia, catastrophic flooding in Peru and Ecuador, and contributed to the warmest year globally ever recorded at that time. The 2015-16 event matched or exceeded those records, causing widespread coral bleaching across the Great Barrier Reef and across reefs worldwide, droughts across southern Africa, and record global temperatures. Each of those events began with subsurface warming that looked, at the corresponding stage, somewhat like what we're seeing now. Each of them was fueled by a collapse of the preceding La Niña and a rapid reversal of trade wind patterns. Each of them surprised forecasters with the speed of their development. What is currently unusual about the developing situation is that the subsurface warming is outpacing the surface warming. The heat building below the thermocline is advancing faster than the sea surface temperature anomalies are responding. Forecasters view this as a sign that the surface has not yet caught up to what is happening below. When the atmosphere and the ocean begin coupling more strongly, when the surface finally responds to the heat below, the warming could be rapid. Not gradual, rapid. The trade winds across the equatorial Pacific are already weakening. This is critical. Weakening trade winds reduce the pressure holding warm water in the western Pacific. They allow the warm subsurface reservoir to begin migrating eastward. They are the atmospheric trigger that transforms a subsurface anomaly into a full El Niño event. And right now, those winds are losing their grip. The Pacific looks calm on the surface, but what is building below it is anything but calm, and the surface is about to find out. Part 3. The Kelvin Wave Engine. There is a delivery mechanism operating beneath the Pacific Ocean right now, and most people have never heard of it. It is called an equatorial Kelvin wave, and understanding it is the key to understanding how El Niño events actually develop from subsurface potential into surface reality. Picture the equatorial Pacific as a long corridor stretching roughly 14,000 kilometers from the coast of Indonesia to the coast of Ecuador. The corridor is filled with water of varying temperatures, warmer near the surface and toward the west, cooler at depth and toward the east. Now imagine that a burst of westerly winds blowing from west to east rather than the normal east to west trade wind direction, suddenly pushes on the surface of that corridor. That push does something remarkable. It forces warm surface water downward and eastward, creating a pulse of warm water that travels along the equator beneath the surface, moving at speeds of roughly 2 to 3 meters per second. That pulse is a Kelvin wave. Kelvin waves are not small events. A single downwelling Kelvin wave can deepen the warm layer of the ocean by tens of meters across a path thousands of kilometers wide. They travel the entire length of the equatorial Pacific in roughly 2 to 3 months. And when they arrive at the coast of South America, they do something that directly triggers El Niño. They suppress the cold water that normally wells up near the coast, replacing it with warm water. Sea surface temperatures rise. The thermocline tilts. The ocean atmosphere coupling that defines El Niño begins to strengthen. How do scientists detect something invisible beneath thousands of kilometers of ocean? The answer is elegant. Warm water is slightly less dense than cold water, which means it occupies slightly more volume. A column of ocean topped by warm water sits just a few centimeters higher than a column topped by cold water. Satellites equipped with radar altimeters can measure these tiny differences in sea level height with extraordinary precision. When a Kelvin wave passes, it leaves a signature in the satellite data, a slight bulge in sea surface height moving eastward along the equator, tracing the path of the warm pulse below. Current satellite data shows active Kelvin wave propagation underway in the equatorial Pacific. The subsurface cross-section diagrams that oceanographers use to visualize what is happening below the surface show large anomalous warm pockets moving eastward at depths between 50 and 200 meters. This is the delivery system carrying the subsurface reservoir toward South America and toward the surface. The parallel to the 2015-16 El Niño is hard to ignore. That event was characterized by a succession of powerful Kelvin waves moving across the Pacific in rapid sequence throughout 2014 and 2015. Each wave added more warm water to the eastern Pacific. Each wave reinforced the weakening of the trade winds. Each wave made the next wave more likely. Scientists call this a positive feedback loop. The ocean and the atmosphere began talking to each other, and the conversation kept escalating. The current subsurface heat content anomaly appears larger than the comparable period before the 2015-16 event. That sentence should probably be read twice. Larger than the period before one of the strongest El Niño events in the historical record. But here is where intellectual honesty requires a pause. Kelvin waves are necessary but not sufficient to produce a major El Niño. The history of ENSO forecasting contains a cautionary tale that every climate scientist knows well. In 2014, a powerful Kelvin wave propagated across the Pacific. Models screamed El Niño. Forecasters warned of a potentially historic event. And then the atmosphere failed to cooperate. The trade winds reasserted themselves. The surface warming stalled. The event fizzled. 2014 became the El Niño that never happened, and it became a permanent reminder that the ocean and the atmosphere must work together to produce a full El Niño. The ocean cannot do it alone. What forecasters are watching for now, over the coming weeks and months, is whether additional Kelvin waves form and propagate across the Pacific. Each sustained westerly wind burst in the western Pacific can generate another pulse. If multiple waves propagate in sequence this spring, the surface warming could accelerate dramatically by summer. The subsurface reservoir would have its delivery mechanism confirmed, and the summer of 2026 could look very different from anything most people alive today have ever experienced. Something is being delivered across the Pacific right now. The question is, what happens when it arrives? Part 4. The heat wave that shouldn't exist. In March 2026, meteorologists across the western United States are watching a temperature forecast that makes no intuitive sense. Phoenix, Arizona is looking at temperatures approaching 105 degrees Fahrenheit. Las Vegas, Nevada is near 100 degrees. Los Angeles, California is approaching 100 degrees. These are not summer temperatures. These are not even late spring temperatures. These are values that in normal years would be remarkable in June. They're occurring in March, 3 months early. To understand why this is extraordinary, consider what March normally looks like in the desert southwest. Average high temperatures in Phoenix in March run around 75 to 80 degrees Fahrenheit. 105 degrees is not a deviation from normal, it is a different climate. It represents an anomaly so far beyond seasonal expectations that many meteorologists are struggling to find appropriate historical comparisons. The mechanism driving this event is a massive high-pressure ridge parked over the western United States. Ridges like this are not unusual, but the intensity and persistence of this one is. High-pressure systems cause air to sink and compress. Sinking air warms as it compresses, in a process called adiabatic heating. Clear skies allow solar radiation to pour onto the surface without interruption. The combination of compressional warming and unfiltered solar input produces temperatures that keep climbing day after day. Meteorologists sometimes call an unusually persistent and intense ridge like this one a heat dome, and that term has been in the news before. The most instructive historical comparison is the June 2021 Pacific Northwest heat dome. That event broke temperature records across Oregon, Washington, and British Columbia by margins so large that scientists initially questioned whether the instruments were calibrated correctly. Temperatures that had never been recorded in human history across those regions arrived in a single long weekend. The event killed hundreds of people, buckled roads, and warped rail lines. It forced a fundamental reassessment of how extreme heat events form and how far outside historical experience they can reach. The current Western US heat dome in March 2026 is occurring 3 months earlier in the calendar year than that event. If the 2021 event seemed incomprehensible for June, what does 105 degrees in March mean? The snowpack across the Sierra Nevada and the Rockies, which normally persists well into spring and supplies water to tens of millions of people throughout the summer, is being obliterated. Water resource managers who plan around snowpack are watching their assumptions evaporate in real time. Wildfire risk is spiking in regions that are not supposed to be at peak fire danger for another several months. Emergency management offices across the region are already activating elevated readiness postures. The warming of the oceans along the west coast, where several marine heat waves have been observed in recent months, appears to be disrupting the normal cooling effect that the Pacific usually exerts on coastal temperatures. Air masses arriving from the ocean are arriving warmer than historical averages, removing one of the traditional brakes on inland heat development. Some meteorologists have begun discussing whether the warm Pacific anomalies already building offshore are beginning to influence the atmospheric circulation patterns over the western United States. This is a delicate claim to make. The full El Niño event has not yet formed. The official thresholds have not been crossed, but the ocean is already anomalously warm, and the atmosphere responds to what is actually there, not to what official classifications have or have not yet declared. What is important to understand is this. The Pacific Ocean has not yet released the stored heat sitting in that massive subsurface reservoir. The truly dramatic phase of this story has not started. The western US is experiencing record-shattering heat in March 2026 while the Pacific is still in the warm-up act. The Pacific subsurface heat is still below the thermocline. The Kelvin waves are still in transit. The trade winds are still weakening but not yet collapsed. The question that hangs over every meteorologist watching these forecasts is an uncomfortable one. If the atmosphere is already this energized, this volatile before El Niño has even fully arrived, what is the atmosphere going to look like when the Pacific finally releases what it has been storing? Part 5. Weather Whiplash Week. Sometimes the atmosphere decides to make a point so emphatically that even the most cautious scientific communicator has trouble using measured language. The same week in March 2026 that Phoenix was approaching 105 degrees Fahrenheit, the central United States was being torn apart by one of the most violent severe weather outbreaks of the year. 17 tornadoes touched down across the Midwest in a single event. One of them, classified as an EF3 with winds estimated at 150 miles per hour, stayed on the ground for 81 minutes and carved a path 37 miles long. That is not a brief violent touchdown. That is a tornado that travelled the length of a mid-sized city and kept going, chewing through everything in its path with the kind of sustained fury that storm chasers spend entire careers hoping never to encounter up close. A hailstone reported in Illinois during the same outbreak measured 6 inches in diameter. 6 inches. If confirmed, that would represent a potential state record. For reference, a standard can of soup is roughly 3 inches tall. This was 2 of those stacked on top of each other, falling from the sky at terminal velocity. The physics of a 6-inch hailstone are worth pausing on. At that size, the stone weighs roughly 1 pound. It falls at speeds approaching 100 miles per hour. It does not bounce. It does not skip. It arrives with the kind of kinetic energy that punches through car rooftops, shatters windshields, and leaves craters in the ground. Over 350 storm reports were filed across the United States in a single day during this outbreak. More than 140,000 customers lost power. Insurance adjusters were still mobilizing when the next wave of storms was already forming on radar. At the same time that violent convective weather was erupting across the Midwest, a blizzard system was developing across the upper Midwest, bringing heavy snow and strong winds to regions just a few hundred miles north of the tornado outbreak. Snow and tornadoes simultaneously separated by a drive that would take you through both in an afternoon. This is one of those atmospheric facts that sounds like an exaggeration until you look at a map. The same country, on the same day, was producing conditions associated with the height of winter and conditions associated with the most dangerous afternoon of tornado season. Residents in Minnesota were shoveling snow, while residents in Missouri were sheltering in basements. The jet stream separating these two worlds was not a gentle gradient. It was a sharp, energized boundary, the kind that meteorologists describe as a loaded gun waiting for a trigger. And while the Midwest was dealing with tornadoes and blizzards, the West was broiling. 100-degree heat in Los Angeles. Record-breaking warmth across the desert Southwest. Snowpack disappearing across mountain ranges that supply water to tens of millions of people. The Sierra Nevada, which functions as a frozen reservoir for California's water supply through the dry summer months, was losing its snowpack weeks ahead of schedule. Water resource managers who build their entire planning frameworks around snowpack measurements were watching their models become unreliable in real time. River flows that should have been running cold and full from winter accumulation were running thin. Reservoirs that should have been filling were not filling at the pace that historical averages predicted. The wildfire risk implications of early snowpack loss are not subtle. California's most destructive fires in modern history have occurred in years when drought conditions arrived early and vegetation dried out faster than normal. When the snowpack disappears ahead of schedule and temperatures are running 15 to 20 degrees above seasonal norms in March, the fuel moisture content of grasses and shrubs drops well before fire agencies have their full, seasonal resources deployed. The margin for error narrows before the season has technically begun. But wait, there was another layer to this week. A geomagnetic storm arrived at Earth, driven by solar wind from an active region on the Sun. Auroras were visible far south of their usual range, appearing over states that rarely or never see them under normal solar conditions. Residents across the northern tier of the United States and into the mid-Atlantic states stepped outside and saw curtains of green and red light in skies that had no business displaying them on a weeknight in March. The spectacle was genuinely beautiful. The cause was not entirely benign. Satellite operators were making adjustments for increased atmospheric drag as the upper atmosphere expanded slightly in response to the solar energy input. Minor fluctuations were being monitored on power grid infrastructure in high-latitude regions. Operators of precision GPS systems were noting degraded accuracy. 4 distinct and extreme atmospheric, oceanic and space weather events were occurring simultaneously, each one independently newsworthy, each one requiring its own team of specialists to monitor and respond to. The question that meteorologists found themselves unable to fully answer was a simple one: is this normal? The honest response from the most careful and experienced observers was something like, individually, each of these events has precedent, but all 4 in the same week at these intensities, during what should be a relatively quiet transition between winter and spring, is unusual in ways that are difficult to quantify, precisely because the observational record of such combinations is limited. Meteorologists have a name for the kind of pattern that produces simultaneous extremes in different regions. They call it weather whiplash. The term captures something real about how the atmosphere behaves during periods of transition and amplification. When the jet stream adopts a highly amplified pattern, with large northward ridges and southward troughs rather than a relatively smooth flow around the hemisphere, the contrast between adjacent weather regimes becomes extreme. A powerful ridge over the west can simultaneously force a powerful trough over the centre of the country. The ridge produces the heat dome, the trough produces the severe weather and the blizzard. They are not unrelated events. They are different parts of the same atmospheric configuration, 2 expressions of a single distorted jet stream pattern that has stretched itself into an extreme shape. Understanding why the jet stream amplifies matters here. The jet stream is driven fundamentally by temperature contrast between the tropics and the poles. Warmer tropics and a warming Arctic can change those contrasts in ways that alter how the jet stream behaves. A more amplified jet stream, one that meanders in larger north-south waves rather than flowing in relatively straight west-to-east bands, tends to produce more persistent and more extreme regional weather patterns. The ridge stays longer, the trough digs deeper, the heat dome bakes the same region for days rather than moving through in 48 hours. The severe weather corridor remains active longer. The duration and intensity of extremes increases even if the frequency of the underlying pattern does not change dramatically. ENSO transitions, the periods when the climate system is shifting between La Niña and El Niño, are known to be associated with highly variable and sometimes amplified weather patterns. The ocean-atmosphere coupling is in flux. Energy is being redistributed across the climate system. Teleconnections, the long-distance relationships between tropical sea surface temperatures and mid-latitude weather patterns, are changing their character. The atmospheric bridges that normally connect the tropical Pacific to weather patterns over North America are reorganizing themselves. During this reorganization, the normal seasonal signals that meteorologists rely on to make extended forecasts become less reliable. The atmosphere is transitioning between 2 states, and transitions are inherently unstable. None of this proves a direct causal chain between the developing Pacific situation and any specific tornado or hailstone in Illinois. Causation in complex systems is rarely that clean. A scientist who claimed with confidence that the subsurface Pacific heat reservoir directly caused a particular EF3 tornado in the Midwest would be overstepping what the data supports. The connection, if it exists, is probabilistic and systemic rather than direct and mechanical. What the Pacific's transition does is change the background conditions. It shifts the probabilities. It tilts the atmospheric dice in ways that make certain extreme outcomes more likely, without making any individual outcome inevitable. But here is what is undeniable. The atmosphere in March 2026 is behaving like a system carrying an unusual amount of energy. The contrasts are too sharp. The extremes are too simultaneous. The jet stream is too amplified. The tornado outbreak, the blizzard, the heat dome, and the geomagnetic storm are not four separate stories that happen to share a calendar week. They are four different instruments in the same orchestra, playing from the same score, conducted by an atmosphere that has been given more energy than it knows how to distribute quietly. Scientists study these atmospheric patterns not to assign blame to a single cause, but to understand the state of the system. A system this energized, this volatile, before the primary driver of global climate variability is even fully activated, is a system worth paying very close attention to. The atmospheric conditions of this single week in March 2026 are, in a sense, a preview, a trailer for a feature that has not yet arrived. The Pacific engine is still building power, the subsurface reservoir is still loading, the Kelvin waves are still in transit, the trade winds are still in the process of losing their grip. What the atmosphere just demonstrated, in the most emphatic terms available to it, is that it does not need El Niño to be fully formed before it starts responding to what is coming. It is already responding. It is already amplified. It is already producing the kind of week that emergency managers remember for years. The Pacific is still building. The atmosphere is already answering. And the spring that separates now from the full story has barely begun. Part 6. Earth's weakening magnetic shield. There is a region above the South Atlantic Ocean where Earth's magnetic field is significantly weaker than everywhere else on the planet. It sits roughly above the ocean between South America and Southern Africa, and it has been growing for decades. Scientists call it the South Atlantic anomaly, and it is one of the more quietly consequential features of the planet we inhabit. Quietly consequential is the right phrase, because this is not a phenomenon that makes headlines the way a hurricane does, or generates the kind of images that spread across social media. It is invisible, it is gradual, and it is, by several measurements, accelerating in ways that were not fully apparent until recently. Earth's magnetic field functions as a shield. It deflects charged particles streaming from the sun, the continuous flow of protons and electrons that make up the solar wind, redirecting them toward the polar regions where they spiral down and produce auroras. The field extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere that surrounds the entire planet. Without this shield, the surface of the planet would receive a significantly higher dose of energetic particle radiation with every solar event. Over geological time, the field has done something even more fundamental. It has kept the atmosphere from being gradually stripped away by the solar wind. Mars lost most of its atmosphere over billions of years, in part because it lacks a global magnetic field strong enough to protect it. Earth kept its atmosphere, its oceans, and eventually its complex life, in part because of a magnetic field generated by processes occurring nearly 3,000 kilometers below the surface. It is, in a very real sense, one of the reasons complex life exists here at all. The South Atlantic anomaly is a region where this shield has a dent in it, not a small dent, a significant, measurable, operationally relevant depression in the field strength that covers an area roughly the size of a continent. Satellites passing through this region encounter significantly higher levels of radiation than they encounter anywhere else in their orbits. The difference is not marginal. Instruments that function normally everywhere else on a satellite's orbital path begin experiencing elevated particle flux when passing through the anomaly. Electronics that are hardened against normal space radiation levels can experience single-event upsets, temporary malfunctions caused by a high-energy particle passing through a circuit and flipping a binary state from 0 to 1 or 1 to 0. At sufficient radiation doses, cumulative damage to electronic components can shorten satellite lifespans. The Hubble Space Telescope routinely shuts down non-critical instruments during its passes through the anomaly to protect sensitive electronics. This is not a precautionary measure taken out of excessive caution. It is an operational necessity based on documented instrument anomalies that occurred before the shutdown protocol was implemented. The engineers who designed Hubble's operational procedures learned through experience that the anomaly required specific accommodation. Astronauts aboard the International Space Station report seeing flashes of light with their eyes closed when passing through the anomaly, caused by cosmic ray particles striking the retina directly. This phenomenon, known as cosmic ray visual phenomena, has been documented since the Apollo missions. Astronauts in low Earth orbit passing through the anomaly experience it more frequently than anywhere else in their orbit. These are not metaphors or theoretical concerns. These are documented, measured, operationally significant effects that engineers and mission planners account for every single day. Data from the European Space Agency's SWARM satellite mission, a constellation of 3 satellites launched specifically to study Earth's magnetic field with unprecedented precision, has revealed that the anomaly is not simply sitting still. It is changing. Over the past decade, measurements from SWARM have shown complex structural evolution that was not detectable with earlier, less precise instrumentation. The anomaly has split into 2 distinct lobes, a pattern that indicates the underlying magnetic structure is becoming more complex rather than simply weakening uniformly across a single region. One lobe sits roughly where the anomaly has historically been centered, over the South Atlantic. The second lobe has developed further to the south and east, over the southern tip of Africa and the surrounding ocean. Field strength measurements show localized weakening of hundreds of nanoteslas over several years in specific regions within the anomaly. To put that in context, the total field strength at the Earth's surface ranges from roughly 25,000 to 65,000 nanoteslas depending on location. Localized changes of hundreds of nanoteslas over a decade represent a meaningful fraction of the regional field strength, not a trivial fluctuation. To understand what is driving this, you have to go to the core of the planet, literally. Earth's magnetic field is generated by the motion of liquid iron in the outer core, approximately 2,900 kilometers below your feet. The outer core is a shell of molten iron and nickel surrounding the solid inner core, and it is in constant motion. Convection currents in that liquid iron, driven by the planet's internal heat escaping outward and by the rotation of the Earth, act like a giant dynamo, generating electrical currents that in turn produce the magnetic field. The process is self-sustaining but not perfectly stable. The convective patterns in the liquid iron are complex, turbulent and changing on timescales, ranging from years to millions of years. Changes in the field at the surface are echoes of what is happening in that liquid iron system, thousands of kilometers down, transmitted upward through the solid mantle in a kind of slow-motion broadcast from the planet's interior. Geophysicists have identified what they call reverse flux patches at the core mantle boundary, regions where the magnetic field is oriented in the opposite direction from the dominant global field. Instead of pointing from south to north, as the main field does, these patches point the other way, locally cancelling or reducing the overall field strength in the regions above them. These patches appear to be growing in size and strength. The South Atlantic anomaly is thought to be the surface expression of one of these reverse flux patches growing beneath the South Atlantic and southern Indian Ocean regions, its influence propagating upward through the mantle and expressing itself as the weakened field we measure at the surface and in low Earth orbit. This connection to core dynamics is important because it means the anomaly is not a surface phenomenon with a surface explanation. It is a window into processes occurring at the very centre of the planet, driven by the same liquid iron convection that has been generating Earth's magnetic field for billions of years. The fact that those processes are producing an increasingly complex surface signature, a splitting anomaly rather than a simple uniform weakening, suggests that the underlying core dynamics are themselves becoming more complex in this region. Whether that complexity represents a temporary fluctuation or a longer-term trend in core behaviour is something that geophysicists are actively debating with the benefit of the best magnetic field data ever collected. This is not a small-scale, easily dismissed phenomenon. Regulatory agencies that oversee satellite operations treat the anomaly as a practical engineering challenge that requires active management. Satellite manufacturers design radiation hardening specifications with the anomaly in mind. Mission operators build anomaly passes into their operational planning. The field is measurably changing on decadal timescales, fast enough that the changes are detectable within the operational lifetime of individual satellites. And the pattern of change, the splitting into 2 lobes, the regional intensification of weakening, is more complex than was apparent before the SWARM mission began delivering its high-precision global field measurements. The scientific community is careful to note that none of this poses any direct danger to people on the ground. The anomaly affects satellites in low Earth orbit because they are above the bulk of the atmosphere and directly exposed to the particle radiation environment. At the surface, the atmosphere provides substantial shielding, even where the magnetic field is weaker than average. The field would have to weaken by a far larger fraction, globally and not just regionally, before ground-level radiation exposure became a meaningful health concern. That is not the situation today, and the evidence does not suggest it is imminent. But here is the question that sits at the edge of mainstream scientific discussion, the one that a small number of serious researchers are beginning to examine with the tools that are now available. Could changes in Earth's magnetic environment influence how the planet interacts with the solar energy, continuously arriving from 93 million miles away? The magnetic field does not just deflect harmful particles, it shapes the geometry of how all charged particles from the Sun interact with the upper atmosphere. Could a weakening or structurally changing magnetic field alter the way energetic particles deposit energy in the stratosphere and upper troposphere? Could those energy deposition changes influence atmospheric chemistry, or circulation patterns, or the formation of clouds at high altitudes? These are not questions with settled answers. They are not questions that mainstream climate science has placed at the centre of its research agenda, but they are questions that the data now makes it possible to ask with more precision than ever before, and a small number of serious researchers are actively exploring them. 3 major planetary systems are showing simultaneous unusual behaviour. The Pacific Ocean, with its unprecedented subsurface heat reservoir and rapidly escalating El Niño forecasts. The Sun, with its dramatically overperforming solar cycle and persistently elevated activity. And Earth's own magnetic field, developing its most structurally complex anomaly in the satellite measurement record, driven by processes occurring nearly 3,000 kilometers below the surface. Whether these represent independent coincidences or something more connected is a question worth holding with care, not with alarm, not with a kind of pattern-seeking that finds meaning in every cluster of events, but with genuine scientific curiosity, the kind that asks whether 3 simultaneous anomalies in interconnected planetary systems might be telling us something about interactions we have not yet fully characterized. The instruments are better than they have ever been. The data is richer than it has ever been. And the questions the data is raising are more interesting than they have been in a very long time. Part 7. The solar cycle that refused to behave. Every 11 years on average, the Sun goes through a cycle. Sunspot counts, which track regions of intense magnetic activity on the solar surface, rise from a minimum to a maximum and back again. Solar flares, those enormous eruptions of electromagnetic energy, become more frequent near the peak. Coronal mass ejections, massive clouds of charged plasma flung into space at millions of kilometers per hour, happen more often. The Sun, in short, becomes more active, and then, following a pattern that has been documented across centuries of astronomical observation, it quiets back down. Sunspot counts fall. Flare frequency drops. The solar wind settles into a calmer, more predictable rhythm. This is the cycle. It is one of the most reliable periodic phenomena in the solar system, ticking along with enough regularity that scientists can plan satellite missions, space weather monitoring programs, and long-term infrastructure protection strategies around its expected behavior. The key word in that sentence is expected. Solar Cycle 25, the current cycle, began around December 2019 and was initially forecast to be a relatively weak and unremarkable event. The panel of solar scientists tasked with making that prediction was not a casual group. It was a formal international collaboration involving dozens of experts from NASA, NOAA, and equivalent agencies around the world, drawing on every available dataset and forecasting methodology. They looked at precursor indicators, measurements of the Sun's polar magnetic field strength that have historically correlated with the strength of the following cycle, and they concluded that Cycle 25 would be similar in strength to Cycle 24. Cycle 24 had itself been one of the weaker solar cycles in approximately a century, a quiet, subdued period of solar activity that produced relatively few major geomagnetic events and gave satellite operators and power grid engineers a prolonged period of relatively benign space weather. The prediction panel expected more of the same, a modest, well-behaved cycle, background solar activity, nothing that would require emergency preparedness planning or generate auroras over populated mid-latitude regions. The Sun had other ideas. Sunspot counts began climbing faster than the projected trajectory. Within the first 2 years of the cycle, it was already clear that the forecast was going to underperform reality. By the middle years of the cycle, the discrepancy between prediction and observation had become impossible to minimize. Sunspot counts climbed higher than projected. The rate of major flare production exceeded expectations. Solar maximum, the peak of activity in the cycle, was officially declared around 2024 and 2025, and by the metrics used to measure solar cycle strength, including smoothed sunspot numbers, flare counts, and geomagnetic activity indices, Cycle 25 turned out to be significantly more active than the prediction panel had anticipated. Not marginally more active, significantly. This is not a minor discrepancy that falls within the normal uncertainty range of solar forecasting. This is the Sun performing well outside the bounds of expert expectation, in a domain where those experts had access to every available tool and dedicated considerable institutional effort to getting the forecast right. The failure of the Cycle 25 forecast is worth dwelling on, not to criticize the scientists involved who are working at the frontier of what solar physics currently understands, but because it reveals something important about the limits of our predictive capability for the star that controls the energy budget of our entire planetary system. If the Sun can dramatically outperform a carefully constructed expert consensus forecast for an 11-year cycle, it is a reminder that the processes driving solar magnetic activity are not yet fully understood. The dynamo operating inside the Sun, the mechanism that generates the cycling magnetic field responsible for sunspots, flares, and the solar wind, remains an active area of theoretical and observational research. Predictions based on that incomplete understanding will sometimes be wrong in significant ways. More importantly, for the current moment, solar activity has not quieted down the way cycles typically do after their peak. The declining phase of a solar cycle is usually characterized by falling sunspot counts, decreasing flare frequency, and a gradual return to the quieter conditions of solar minimum. That decline is underway in a nominal sense, but it is not proceeding at the pace or to the depth that historical cycle comparisons would suggest. High sunspot counts have persisted. Active regions on the solar surface, the magnetically complex areas where field lines twist and interact and occasionally release enormous amounts of stored magnetic energy, have continued emerging and producing significant events. X-class flares, which sit at the top of the classification system used to rank solar events by their X-ray output intensity, have continued occurring at a rate that keeps space weather forecasters in a state of elevated alertness. Coronal mass ejections have continued impacting Earth's magnetosphere at a frequency that keeps satellite operators, power grid engineers, and anyone responsible for high-latitude infrastructure paying close attention to the daily space weather forecast. One particular phenomenon deserves more public attention than it typically receives. Coronal holes are regions on the Sun where the solar corona, the outer atmosphere, has open magnetic field lines rather than the closed-loop structures that dominate most of the solar surface. Through these open field lines, the solar wind escapes at much higher velocities than it does from the rest of the Sun. A typical solar wind speed might be around 400 km per second. A high-speed stream from a coronal hole can arrive at Earth travelling at 700 to 800 km per second or faster. When Earth passes through one of these high-speed streams, the interaction with their magnetosphere can produce sustained geomagnetic disturbances that last for days, even without a major flare or coronal mass ejection driving them. Auroras appear at lower latitudes than usual. Satellites in low Earth orbit experience increased atmospheric drag as the upper atmosphere expands in response to the increased energy input. Sensitive electronics on satellites can experience single-event upsets. GPS accuracy degrades. High-frequency radio communications used by aviation experience disruption at high latitudes. These are not catastrophic events, but they are not trivial ones either, and they are occurring more frequently than the Cycle 25 forecast suggested they would. Historical precedent introduces a further complication that makes the current situation more concerning, not less. Some of the most powerful and damaging geomagnetic storms in the modern era did not occur at solar maximum. They occurred during the declining phase of the solar cycle, months or years after the peak had passed. The Halloween storms of 2003 are the canonical example. Those events, which occurred in late October and early November of that year, produced X-class flares of extraordinary intensity, including what is estimated to have been one of the most powerful solar flares ever recorded, partially saturating the instruments designed to measure it. the associated geomagnetic storms damaged power transformers in Sweden and South Africa. They temporarily disabled or degraded multiple satellites in orbit. They forced the International Space Station crew to shelter in a more radiation-protected section of the station, and they produced auroras visible as far south as Texas, Florida, and the Mediterranean coast of Europe. All of this occurred not at the peak of solar cycle 23, but during its declining phase, when many observers had assumed the most dangerous period had passed. The physical reason for this pattern is not entirely settled science, but the leading explanation involves the geometry of the solar magnetic field during the declining phase. As the cycle winds down, large coronal holes tend to develop at lower latitudes than they occupy near solar minimum, placing their high-speed streams in a geometry that intersects Earth's orbit more frequently and at higher impact angles. Simultaneously, the interplanetary magnetic field during declining phase periods can have an orientation that couples more efficiently with Earth's magnetosphere during storm conditions, producing stronger geomagnetic responses for a given level of solar activity than would occur near solar maximum. The result is that the declining phase is, in some respects, the most dangerous phase for Earth-directed space weather impacts. Not the most active phase in terms of raw flare counts, but the phase most likely to produce the specific combination of conditions that causes serious geomagnetic disturbances at Earth. This means that even as solar cycle 25 nominally moves past its peak, the potential for significant and potentially severe geomagnetic events remains elevated, possibly for several more years. The Sun is carrying substantial residual activity from a cycle that already dramatically exceeded expectations. Active regions are still emerging. Significant flares are still occurring. Coronal holes are still producing high-speed streams that sweep past Earth on recurring intervals as the Sun rotates. And Earth's magnetic field, as has already been discussed in the context of the South Atlantic anomaly and the racing magnetic pole, is not in the same condition it was during previous solar cycles. A magnetosphere that is showing structural changes, with a growing and splitting anomaly over the South Atlantic, may respond differently to major geomagnetic storms than historical experience from stronger field periods would predict. Whether that difference is significant enough to matter practically is an open question that space weather researchers are beginning to study with new urgency. The compounding nature of these simultaneous anomalies is the thread that keeps running through this entire story. Any single one of them, in isolation, would be scientifically interesting and worth monitoring carefully. A dramatically overperforming solar cycle is notable. A growing and structurally evolving magnetic field anomaly is notable. A Pacific Ocean building a subsurface heat reservoir with no precedent in the observational record is notable. But all three of these systems showing unusual behavior at the same time, while the atmosphere is already producing extreme weather combinations that meteorologists are struggling to characterize, is something that moves beyond individually notable into collectively significant. The Sun was supposed to be calming down by now. The forecast said so. The historical cycle comparison suggested it. The prediction panel, drawing on every available tool, projected a quiet, unremarkable decline towards solar minimum. Instead, the Sun is still producing X-class flares. Coronal holes are still sending high-speed streams past Earth. The space weather forecast remains active and will likely remain so for years. The Sun is not calming down. The Pacific is loading. The magnetic field is fracturing. The atmosphere is already responding. Add all of that to the list and ask yourself honestly, how many simultaneous anomalies does it take before coincidence stops being a satisfying answer? Part 8. The Magnetic Shield Hypothesis. What follows in this section is not settled science. It is important to say that clearly at the start, before a single speculative claim is made, because the distinction between what is known and what is proposed matters enormously in a story like this one. What follows is a description of a speculative but scientifically serious line of thinking, discussed in some research circles, one that proposes a connection between solar activity, Earth's magnetic field, and the behavior of climate systems like ENSO. Mainstream climate science does not treat solar forcing as a major driver of El Niño. The mechanisms that drive ENSO are well understood in terms of ocean-atmosphere dynamics, and those mechanisms do not require any input from the Sun beyond the baseline solar radiation that has been arriving at Earth for billions of years. This is not a space for conspiracy theories or motivated reasoning, or the kind of breathless extrapolation that conflates correlation with causation. This is a space for an honest account of what some researchers have proposed, why the question remains open, and why the current moment makes it more interesting than it has been in some time. Some scientific papers have examined whether there is a statistical relationship between the solar cycle and the timing of El Niño events. These papers exist in the peer-reviewed literature. They are not fringe publications or preprints posted without scrutiny. They are careful, methodologically serious analyses that have asked a straightforward empirical question. Do El Niño events occur more often or with greater intensity during certain phases of the solar cycle? The results are not definitive. Anyone who tells you they are in either direction is overstating what the data supports. But the results are not entirely dismissive either. Several analyses have identified patterns suggesting that El Niño events may occur with slightly elevated frequency in the 1 to 3 years following solar maximum. The pattern is not strong enough to be a reliable forecasting tool. It is not the kind of signal that would allow a climate scientist to say with confidence that a strong El Niño is coming, because solar maximum just passed. But it is a signal that appears in multiple independent analyses using different data sets and different methodological approaches, which means it is not simply an artifact of one research group's particular choices. The proposed mechanisms connecting solar activity to ENSO behavior are multiple, and they operate through different physical pathways. The first and most studied involves the stratosphere. During periods of high solar activity, the sun's output of ultraviolet radiation increases by a larger percentage than its total energy output. While total solar irradiance changes by only about 0.1% across a solar cycle, ultraviolet output can change by several percent. Ultraviolet radiation is absorbed primarily in the stratosphere, where it drives the chemistry that creates and destroys ozone. When ultraviolet output increases, it warms the stratosphere slightly, and that warming is not uniform. It tends to be concentrated in certain latitude bands and at certain altitudes, altering the temperature gradients that drive the large-scale atmospheric circulation waves known as planetary waves or Rossby waves. These waves connect the stratosphere to the troposphere below, and they connect the tropics to the mid-latitudes through a process called downward propagation. If solar-driven stratospheric warming changes the character of these waves, even subtly, it could influence the surface pressure patterns and wind fields that govern the tropical Pacific Ocean atmosphere system. This is a physically plausible chain of causation. Each link in the chain is individually defensible. Whether the chain is strong enough to produce a detectable influence on ENSO is the question that remains unresolved. The second proposed mechanism involves more direct solar heating of the tropical ocean surface. This pathway is more difficult to defend energetically because the total change in solar irradiance arriving at the tropical Pacific surface across a solar cycle is genuinely small. The tropical Pacific is an enormous heat reservoir with substantial thermal inertia. A 0.1% change in incoming solar radiation is a small perturbation to a large system. Climate scientists who have studied this carefully and honestly point out that this energy change is small compared to the energy fluxes that drive ENSO dynamics, which involve the redistribution of heat already stored in the ocean, rather than new energy inputs from above. The ocean atmosphere system is simply too large and too energetically dominated by internal dynamics for a small solar variation to serve as the primary trigger of an El Niño event. On this point, the mainstream scientific consensus is on solid ground, and the burden of proof on those proposing a direct solar heating mechanism is appropriately high. But here is where the question gets more interesting and more subtle. The framing of the debate as solar forcing versus internal ocean atmosphere dynamics may be a false dichotomy, not whether the sun causes El Niño, which it almost certainly does not in any primary sense, but whether the sun can modulate it. Whether solar activity at certain phases of the cycle can act as a small but potentially decisive nudge to a climate system that is already poised on the edge of a major transition. The concept here is not forcing but tipping. Complex non-linear systems can have tipping points, thresholds where a small additional perturbation pushes the system across a boundary it might not otherwise have crossed, or crosses sooner than it otherwise would have. If the Pacific Ocean atmosphere system is already loaded with subsurface heat, already transitioning from La Niña to El Niño, already showing weakening trade winds and propagating Kelvin waves, then the question of whether a small solar-driven stratospheric nudge could influence the timing or intensity of the resulting event becomes genuinely interesting in a way it would not be if the Pacific were in a neutral, unloaded state. The second dimension of this question involves Earth's magnetic field, and this is where the speculation becomes most frontier and most carefully qualified. The magnetic field shapes the geometry of how charged particles from the Sun interact with the upper atmosphere. In regions where the field is stronger, charged particles are more efficiently deflected toward the poles. In regions where the field is weaker, like the South Atlantic anomaly, more particles penetrate to lower altitudes before being stopped by the atmosphere. Could a structurally changing magnetic field, one developing its most complex anomaly in the satellite measurement record, alter the spatial pattern of how solar energy is deposited in the upper atmosphere? Could those changes in energy deposition pattern influence stratospheric chemistry, or the temperature gradients that drive planetary waves, or the circulation patterns that connect the stratosphere to the surface? These questions sit at the intersection of space physics, atmospheric dynamics, and climate science, a boundary region where the relevant communities do not always talk to each other as much as they might. The honest answer is that current models do not fully capture these interactions, not because the science is bad or the modelers are negligent, but because characterizing the interactions between the deep Earth system, the surface climate system, and the space environment requires integrating knowledge and computational frameworks across disciplines that have historically developed somewhat independently. What makes the current moment unusual is not that any single one of the anomalies described in this story is unprecedented in isolation. Taken individually, each has an explanation rooted in known physics, with precedents in the historical record and mechanisms that are at least partially understood. A massive Pacific subsurface heat reservoir building toward a potential super El Niño is unusual, but not without historical parallel. Global ocean temperatures at near-record highs reflect the accumulated heat content of a warming ocean system. An overperforming solar cycle reflects the genuine difficulty of predicting solar magnetic activity from incomplete knowledge of the underlying dynamo processes. A magnetic field showing its most complex structural anomaly ever recorded by satellites reflects core dynamics that have been evolving for millions of years. Each of these is a real, documented, measurable phenomenon with its own scientific story. What is unusual is that they are all occurring simultaneously, and that the simultaneous occurrence is happening at a moment when the Pacific is already in a maximally loaded state, when the atmosphere is already producing extreme weather combinations before the primary Pacific signal is even fired, and when the global ocean baseline is already at or near record warmth. The coincidence of timing is what elevates the question from individually interesting to collectively significant. Complex systems have a property that linear thinking does not easily accommodate. It is called emergent behavior. When two or more systems interact, the combined system can produce outcomes that neither system would produce on its own. The behavior that emerges from the interaction is not predictable by studying each system in isolation. The climate system is not a single phenomenon governed by a single set of equations. It is a collection of interacting subsystems, oceanic, atmospheric, magnetic, solar, biological, that influence each other through pathways that range from well-characterized to barely studied. Sophisticated climate models capture many of these interactions with impressive skill. They also necessarily simplify or omit interactions that are difficult to parameterize, interactions that occur at boundaries between disciplines, interactions that require data that has only recently become available. The South Atlantic anomaly's influence on upper atmospheric energy deposition is not a standard term in the equations of a general circulation model. The coupling between solar cycle phase and stratospheric planetary wave behavior is represented in some models and absent from others. These are not criticisms. They are descriptions of the frontier. The hypothesis explored in this section may be wrong. The coincidence of anomalies may be exactly that, a statistical cluster, a run of independent unusual behavior across multiple systems that happens to fall in the same narrow window of time. Complex systems produce apparent patterns regularly. The human mind is extraordinarily good at finding connections, sometimes where genuine connections exist and sometimes where they do not. The scientific disposition toward curiosity is not the same as the motivated reasoning that finds patterns because it wants them to be there. The question deserves to be asked with clear eyes, rigorous methods, and genuine willingness to conclude that the answer is simply coincidence. But the question deserves to be asked: are these systems, the Pacific Ocean, the global atmosphere, the Sun, and Earth's own magnetic field, talking to each other in ways we do not yet fully understand? Are the interactions between them richer and more consequential than our current models capture? Is the Earth system at this particular moment doing something more connected and more complex than 4 independent anomalies happening to share a calendar year? The instruments are better than they have ever been. The data is richer than it has ever been. The computational tools available to study these questions are more powerful than they have ever been. If the answer is out there, this is the moment in scientific history when we are most capable of finding it. The question is whether we are asking it loudly enough. Part 9. The ocean is already at record heat. There is a baseline fact that needs to be clearly stated before discussing what a potential strong or super El Niño would mean for global temperatures. The baseline itself is already extraordinary. Global ocean temperatures have been running near or at record highs since 2023. This is not a regional quirk or a temporary fluctuation driven by a single unusual season in one part of the world. Multiple successive months have recorded the highest global sea surface temperatures ever measured in the instrumental record, a record that extends back to the mid-19th century and has been cross-validated against ship logs, buoy networks, satellite measurements, and ocean sediment proxies. The oceans have been in a historically anomalous warm state for over 2 years, and that anomaly is not showing meaningful signs of reverting to the conditions that characterized the decades before it. The persistence of this ocean warming is what makes it scientifically significant in a way that a single record month would not be. Individual record temperatures occur in complex systems for many reasons, including natural variability, unusual weather patterns, or random clustering of favorable conditions. When records fall for a single month, scientists note it and monitor for follow-through. When records fall for month after consecutive month, across multiple ocean basins simultaneously, over a period spanning more than 2 years, the explanation shifts from natural variability towards something more structural. The ocean system is not fluctuating around its historical mean. It appears to have shifted to a new, higher mean, at least temporarily, and the question of whether that shift is temporary or represents a more permanent transition in the ocean's heat state is one of the most consequential open questions in current climate science. Understanding why the oceans are so warm requires a brief but important look at the physics of how the climate system manages energy. The Earth receives energy from the Sun and must radiate an equal amount back to space to maintain a stable temperature. Increasing concentrations of greenhouse gases in the atmosphere reduce the efficiency of that outgoing radiation, creating an energy imbalance. More energy arrives than leaves. That imbalance has to go somewhere. It does not distribute itself evenly across the planet's surface and atmosphere. The oceans absorb roughly 90% of the excess heat that accumulates in the Earth system as a result of this imbalance. That is not a metaphor or a rough approximation. It is a measured, verified accounting of energy flows derived from Argo float networks, satellite ocean heat content measurements, and careful analysis of ocean temperature profiles at depths ranging from the surface to 2,000 meters and below. The oceans are the thermal buffer of the climate system, the massive heat sink that absorbs the majority of the energy accumulating in the Earth system and prevents it from immediately expressing itself as surface air temperature increases. Without this buffering function, land surface temperatures would be rising significantly faster than they already are. But that buffering function has a consequence that is easy to overlook. The oceans are absorbing an enormous amount of energy every year, and that energy does not disappear. It accumulates in the water column, warming ocean layers at depths that were previously stable on human timescales. The heat content of the global ocean at depths below 700 meters has been increasing measurably. The heat content at depths below 2,000 meters has been increasing. The ocean is not just warming at the surface. It is warming throughout its depth, storing energy in layers that interact with the surface on timescales ranging from years to centuries, depending on the circulation pathways involved. The surface warming we measure is the visible expression of a much larger and deeper process of energy accumulation that has been underway for decades. Marine heat waves are one of the clearest expressions of this accumulated heat manifesting at the surface. Defined as extended periods where ocean temperatures in a given region significantly exceed the historical norms for that location and season, marine heat waves have been observed simultaneously in multiple ocean basins over the past 2 years, in a pattern that has no clear precedent in the instrumental record. The North Atlantic experienced a marine heat wave of extraordinary intensity in 2023, with temperatures running several degrees above average across large areas and breaking records that had stood for decades. The Indian Ocean has experienced persistent above-normal temperatures. The northeastern Pacific, already the site of the famous blob heat wave that disrupted marine ecosystems across the west coast in 2014 and 2015, has seen renewed warming. Waters around Antarctica have been running at anomalously warm temperatures that have concerned glaciologists monitoring ice shelf stability. These are not isolated regional events happening to cluster in the same time period. They are simultaneous expressions of an ocean system that is carrying more heat than it has carried at any point in the period of systematic measurement. The ecological consequences of sustained marine heat waves are not abstractions. Coral reefs around the world are experiencing bleaching events at a scale and frequency that has no parallel in either the historical record or the paleo record reconstructed from coral growth patterns and isotopic analyses. The Great Barrier Reef, the largest coral ecosystem on the planet, stretching over 2,300 kilometres along the northeastern coast of Australia and harbouring extraordinary biodiversity built up over thousands of years, has experienced multiple severe bleaching events in recent years with insufficient recovery time between them. The biology of coral bleaching is straightforward and devastating in equal measure. Corals exist in a symbiotic relationship with photosynthetic algae called zooxanthellae that live in their tissues. These algae provide the coral with up to 90% of its energy through photosynthesis and give coral reefs their characteristic colours. When water temperatures rise above the threshold the coral's physiology can tolerate, typically just 1 to 2 degrees Celsius above the seasonal maximum, the coral expels its symbiotic algae. The coral turns white, bleached, and begins starving. If temperatures return to normal quickly, the coral can reabsorb algae and recover. If elevated temperatures persist, or if bleaching events occur repeatedly before full recovery, the coral dies. Reefs that have been building their carbonate structures for thousands of years can be functionally destroyed in a single prolonged thermal event. Now consider what happens when El Niño arrives on top of this already elevated baseline. One of the most consistent and well-documented effects of El Niño events is a temporary spike in globally averaged surface temperatures. The mechanism is straightforward. El Niño releases stored heat from the Pacific Ocean into the overlying atmosphere, warming the air above the tropical Pacific, and driving temperature increases across large parts of the globe through atmospheric teleconnections. This heat release is not a small signal. The 2015-16 El Niño, superimposed on the already warm background conditions of that era, produced the highest globally average temperatures ever recorded at that time, breaking the previous record by a margin that surprised even researchers who were expecting a record. Global average surface temperatures that year were approximately 1.2 degrees Celsius above pre-industrial levels, a threshold that climate policy discussions had treated as a future boundary. El Niño delivered it as a present tense measurement. The current situation begins from a baseline that is already measurably warmer than the baseline that existed when the 2015-16 El Niño arrived. The oceans going into a potential 2026 El Niño are running warmer than the oceans that fed the 2015 event. The atmosphere going into this potential event is operating in a higher energy state. The background global average temperature against which any El Niño warming pulse would be added is higher than it was a decade ago. If a strong or super El Niño forms in 2026, it would be adding its heat release pulse on top of a system that is already carrying more thermal energy than it held during any previous El Niño in the instrumental record. The arithmetic of that scenario is not complicated, and it is not reassuring. Adding a strong El Niño signal to an already record-warm baseline does not produce a moderate outcome. It produces a new record, potentially by a margin that redefines expectations again. The human consequences of such an event extend well beyond temperature statistics. Agriculture across the tropics and subtropics depends on rainfall patterns that El Niño disrupts reliably and significantly. The Indian monsoon, which provides water to agriculture supporting over 1 billion people, typically weakens during El Niño years. Southern Africa and parts of East Africa experience drought. Northeastern Brazil, a region already prone to water stress, faces reduced rainfall. Meanwhile, the western coast of South America experiences catastrophic flooding. Ecuador and Peru, which sit directly in the path of the warm water surge that defines east-based El Niño events, can receive months of rainfall in days during strong events. The 1997-98 El Niño caused flooding in Peru that destroyed infrastructure that took years to rebuild. Fisheries across the eastern Pacific collapse when the cold, nutrient-rich upwelling waters that normally support Productive marine food webs are suppressed by the anomalously warm surface layer. The Peruvian anchovy fishery, one of the largest single-species fisheries in the world, essentially ceases to function during strong El Niño events. Water resources in regions that depend on El Niño-driven rainfall face shortages that cascade through agriculture, energy generation, and municipal supply systems. The Pacific is not warming in isolation. It is warming as part of a planetary ocean system that has been absorbing heat for decades and is now running warmer than at any point in the human record. Every ocean basin is contributing to and expressing this accumulated energy. Every marine ecosystem is responding to it. Every weather system that forms over anomalously warm ocean water carries more moisture and releases more energy than the historical record suggests it should. The El Niño that may be building in the Pacific is not arriving into the stable climate system that produced the historical averages we use as our baseline for comparison. It is arriving into a system that has already moved beyond those averages in ways that are measurable, documented, and consequential. The baseline has shifted. The event that may be coming would be superimposed on that shifted baseline, and the combination of the two, a potentially historic El Niño arriving into an ocean system already at record warmth, is not a scenario for which the historical record provides a fully adequate guide. We are, in a meaningful sense, navigating with maps drawn for a coastline that no longer quite matches the territory. Part 10. The Spring Predictability Barrier. There is a reason that climate scientists, despite everything the models are showing, are still choosing their words carefully. There is a reason that no major forecasting centre has yet declared a strong El Niño inevitable or a super El Niño definitively on the way, despite model ensembles pointing in directions that would, in any other season, generate considerably more alarm in public communications. The caution is not timidity. It is not institutional conservatism or bureaucratic reluctance to deliver uncomfortable news. It is something more specific and more scientifically justified than any of those explanations. That reason has a name. It is called the Spring Predictability Barrier, and it is one of the most humbling features of ENSO science, a phenomenon that has embarrassed confident forecasters, disrupted careful planning, and forced the entire field to develop a more sophisticated relationship with uncertainty than most branches of applied science are required to maintain. Every year, from roughly March through May, the ability to forecast ENSO conditions several months in advance drops sharply and measurably. This is not a subjective impression held by forecasters who have been burned by spring surprises. It is a quantifiable, statistically documented feature of ENSO predictability that appears consistently across different modelling systems, different forecast methods, and different historical periods. The statistical skill of seasonal models, their demonstrated ability to predict whether El Niño or La Niña conditions will dominate the tropical Pacific by late in the year, decreases during this window to a degree that forecasters treat with genuine respect. Forecasts initialized in January or February carry meaningful skill for the following fall and winter. Forecasts initialized in April or May carry substantially less. The same models, running the same physics, applied to the same ocean, lose predictive power during this specific seasonal window in a way that has been documented extensively and remains only partially explained. The physical reason for the spring predictability barrier involves the character of the ocean atmosphere coupling during this period. Across the equatorial Pacific, the interaction between sea surface temperatures and the overlying atmosphere, the feedback loop through which warm ocean temperatures weaken trade winds and weakened trade winds allow ocean temperatures to warm further, reaches its annual minimum strength during boreal spring. The coupling signal that allows forecasters to project how the system will evolve is at its weakest. The signal-to-noise ratio in the ocean atmosphere system drops. What this means practically is that small disturbances, random fluctuations in wind patterns, a brief reassertion of trade wind strength, an anomalous convective event in the Western Pacific, variations that would be absorbed and overcome by a strongly coupled system, can have outsized effects on the eventual outcome during this window. The system is, in a technical sense, less self-organizing during spring than at other times of year. Its trajectory is more susceptible to perturbation. Conditions that appeared locked in during the preceding winter can unlock with surprising speed when the spring barrier arrives. The infamous 2014 El Niño forecast failure is the cautionary tale that every ENSO forecaster carries with them, the story that gets told in seminars and referenced in papers whenever the temptation arises to express too much confidence in a model ensemble that is pointing strongly in one direction. In early 2014, the situation looked remarkably promising for a significant El Niño event. A powerful downwelling Kelvin wave had propagated across the Pacific in late 2013 and early 2014, the largest such wave in the observational record at that time by some measurements. Sea surface temperatures in the eastern Pacific were rising. Model ensembles were converging on strong El Niño projections with a confidence that was unusual for that lead time. Forecasters at major centres, including NOAA's Climate Prediction Centre and international equivalents, were preparing seasonal outlooks that anticipated a significant, potentially historic event. The global media picked up the story. Agricultural planning offices in El Niño-sensitive regions began adjusting their outlooks. Water resource managers started revising their seasonal projections. Insurance companies began pricing El Niño risk into their models. The expectation of a strong El Niño in 2014 became, for a period, something close to conventional wisdom among people who follow these things. And then the spring predictability barrier arrived, and the atmosphere simply did not cooperate. Trade winds, which had been weakening in a pattern consistent with El Niño development, reasserted themselves across the central and western Pacific at a critical moment in the spring of 2014. The reassertion was not dramatic. It was not a sudden reversal or an extreme anomaly in the opposite direction. It was a relatively modest strengthening of the trade wind field that, under normal circumstances, might not have attracted much attention. But it arrived at exactly the wrong moment, when the ocean-atmosphere coupling was at its seasonal minimum, when the system was most susceptible to perturbation, and it was enough. The eastward migration of warm subsurface water slowed. The surface warming that forecasters had been watching as confirmation of their projections stalled. The positive feedback loop that should have been accelerating El Niño development failed to engage at the required strength. By the middle of 2014, the model ensembles that had been so confidently pointing toward a strong event were beginning to diverge. By late 2014, forecasters were quietly acknowledging in their official communications that the event they had projected was not going to materialize at the intensity or in the time frame that had been forecast. A weak El Niño did eventually develop in late 2014 and persisted into 2015, where it became the precursor to the genuine Super El Niño of 2015 to 16. But the strong event that 2014 was supposed to deliver never arrived. The fuel had been there, the subsurface signal had been there, the model agreement had been there, and the atmosphere had simply declined to play its required role during the critical spring window. The 2014 failure is instructive not because it proves that the current forecasts are wrong, or even that they are likely to be wrong. The current subsurface signal is, by several measurements, larger than the 2014 signal. The model convergence towards strong or super El Niño territory is occurring across more modelling systems and with more internal consistency than the 2014 projections showed. The global ocean baseline is warmer, providing a more energetically favourable environment for El Niño development. None of these factors make a 2014-style outcome impossible, but they do mean the situations are not identical, and the differences favour development rather than failure. What 2014 teaches is not that confident-looking forecasts are wrong. It teaches that they are uncertain, and that the specific nature of that uncertainty during the spring window is qualitatively different from the uncertainty that attaches to forecasts made at other times of year. Even strong subsurface signals and multiple model ensemble convergence cannot guarantee an outcome during this window. The atmosphere retains its own variability. Small noise can amplify into large consequences when the coupling is weak. Conditions that appear locked in during winter, supported by impressive model agreement and compelling observational data, can unlock with a speed that retrospectively looks obvious, but prospectively was not visible in any single indicator. What forecasters will be watching over the coming months is specific, measurable, and well-defined. Trade wind behaviour across the equatorial Pacific is the single most important variable. The trade winds are the atmospheric component of the ENSO feedback loop, and their behaviour during spring will be the clearest early signal of whether the atmosphere is going to couple with the subsurface ocean heat or resist it. If the trade winds continue their current weakening trend, or if they reverse into westerly anomalies across the central Pacific, the subsurface heat reservoir will continue its eastward migration, and surface coupling will strengthen in the way the models are projecting. If the trade winds reassert even modestly, the heat migration could slow or stall long enough to allow the spring barrier to pass without full development, leaving the system in an ambiguous state heading into summer. Kelvin wave activity will be tracked continuously via satellite altimetry, the same sea level height measurements that reveal subsurface warm water pulses moving eastward along the equator. Each new Kelvin wave that forms and propagates across the Pacific this spring adds more warm water to the Eastern Pacific delivery system and makes a failure of development less likely. Sea surface temperature anomalies in the Niño 3.4 region will be monitored on a weekly basis, providing the surface confirmation that forecasters need to see alongside the subsurface signals. Atmospheric pressure differences between Darwin, Australia and Tahiti, the index known as the Southern Oscillation Index that measures the large-scale atmospheric pressure gradient associated with trade wind strength, will be scrutinized for sustained negative values that would indicate a weakening of the trade wind system consistent with El Niño development. And outgoing long-wave radiation measurements over the central and eastern Pacific will be watched for signs of increased deep convection, the atmospheric thunderstorm activity that signals the atmosphere beginning to respond to the warming ocean below. By early summer 2026, the picture should be considerably clearer than it is today. The spring predictability barrier will have passed. The seasonal minimum in ocean-atmosphere coupling will be over. Model forecast skill will improve substantially as initialization dates move past May and into June. And scientists will know, with a degree of confidence that is not currently available, whether the Pacific is genuinely heading toward one of the strongest El Niño events in the modern instrumental record, or whether the system is tracking toward a more modest but still significant event, or whether another 2014-style near-miss is unfolding in which all the ingredients were present, but the atmospheric cooperation never materialized at the required moment. The models are screaming. The subsurface data is, by multiple measures, alarming in its scale and rate of development. The historical analogues that forecasters reach for when trying to contextualize the current situation are the events that define the outer boundaries of what El Niño can do. But the spring has not yet passed. The atmosphere has not yet committed. The Pacific has not yet declared itself in the unambiguous way that removes forecasting uncertainty and replaces projection with observation. Until it does, the honest answer, the scientifically defensible answer, is that we are watching one of the most consequential climate forecasting situations of the modern era unfold in real time, with instruments better than any previous generation of scientists had access to, and the outcome remains genuinely uncertain in ways that matter enormously for billions of people whose agriculture, water supply, and weather patterns will be shaped by what the Pacific decides to do in the next several months. That uncertainty is not a flaw in the science. It is not a failure of the models or the forecasters or the observing systems. It is the science working exactly as it should, maintaining appropriate epistemic humility in the face of a complex nonlinear system that has surprised experts before and retains the capacity to surprise them again. The spring predictability barrier is not an embarrassment to ENSO science. It is one of its most honest features, and right now it is the only thing standing between a strong model signal and a definitive forecast. When it passes, we will know. Until then, we watch. Part 11. The asteroid. We can't properly measure. There is a blind spot in humanity's planetary defense system, and it faces the sun. Any object approaching Earth from the direction of the sun is effectively invisible to ground-based telescopes during its approach. The sun's glare overwhelms optical instruments with a wall of light so intense that even sophisticated modern telescope arrays, capable of detecting galaxies billions of light-years away, cannot reliably distinguish a dark, rocky object a few tens of meters across when it is positioned against that background. Infrared detectors have partial capability but limited sensitivity at distance, offering a partial workaround that closes some of the gap but not all of it. Space-based telescopes in certain orbital configurations can observe the regions of sky near the sun from angles that ground-based systems cannot access, but current space-based assets provide incomplete coverage of the full threat geometry. The result is a genuine, documented, operationally significant gap in our ability to detect certain categories of near-Earth objects before they get close enough to matter. This gap is worth understanding in its full context. The history of planetary defense as a serious scientific and policy discipline is surprisingly short. For most of human history, The idea that a rock from space might arrive without warning and cause regional or global devastation was understood in the abstract, evidenced by impact craters and occasional historical accounts of bolide events, but not systematically studied or monitored. The field of near-Earth object detection as an organised, funded, internationally coordinated enterprise is essentially a product of the last 3 decades. The SpaceGuard survey, initiated in the 1990s following a congressional mandate to NASA, set the first systematic detection goals: find 90% of near-Earth asteroids larger than 1 kilometre in diameter within a decade. That goal was largely achieved. Objects large enough to cause civilization-scale damage are now tracked with reasonable completeness. We know where the truly giant rocks are, and none of them are heading our way in any timeframe that current orbital mechanics can project. But the threat landscape does not begin and end with civilization-ending impactors. The Tunguska event of 1908, in which an object estimated between 50 and 80 meters in diameter exploded in the atmosphere above a remote region of Siberia, flattened approximately 2,000 square kilometers of forest, and released energy equivalent to roughly 10 to 15 megatons of TNT. Had it arrived at a slightly different angle, or over a populated region rather than remote taiga, the human consequences would have been catastrophic, on a scale that would have defined the 20th century differently. The Chelyabinsk event of 2013 involved an object approximately 20 meters in diameter that entered the atmosphere over a populated region of Russia without any prior detection whatsoever. The airburst released energy equivalent to roughly 500 kilotons of TNT, injured over 1,500 people primarily from shattered glass, and caused significant structural damage across a wide area. Neither of these objects was detected before it arrived. Neither was on any watch list. Neither gave any warning. This is not a theoretical concern dressed up in hypothetical language. Scientists have documented multiple cases in recent years of asteroids discovered only days or even hours before their closest approach to Earth. Some of these objects were significant in size, well above the threshold at which atmospheric entry would produce a damaging airburst, rather than burning up harmlessly. One notable documented example involved an asteroid roughly 20 meters in diameter that passed within approximately 40,000 kilometers of Earth and was discovered less than 24 hours before its closest approach. 24 hours. For context, 40,000 kilometers is roughly 10 times the distance to geostationary communication and weather satellites. It is not the surface of the Earth. A pass at that distance is not an impact. But on astronomical scales, where the distances between planets are measured in hundreds of millions of kilometers, 40,000 kilometers is an extremely close approach, and the discovery timeline of less than a day represents essentially zero warning time for any kind of coordinated response. Size estimation for newly discovered asteroids compounds the challenge in ways that are not immediately obvious to non-specialists. When a ground-based optical telescope detects a previously unknown object, the primary measurement available is the amount of light the object reflects toward the telescope. This measurement, called the apparent magnitude, depends on 2 things that cannot be independently determined from a single brightness observation: the physical size of the object and its surface reflectivity, or albedo. An asteroid with a highly reflective surface, perhaps covered in bright minerals or fresh rocky material, exposed by a recent collision, will appear brighter than a physically larger asteroid with a dark, carbon-rich surface that absorbs most of the sunlight hitting it. 2 asteroids of identical size but different surface compositions can reflect dramatically different amounts of sunlight, producing apparent magnitudes that differ by factors that translate into size estimate errors of 2 or more in either direction. An object estimated at 50 meters in diameter based on its brightness could be 25 meters or 100 meters, depending on its albedo, and those 3 sizes carry very different consequences for what happens if the object enters Earth's atmosphere. Radar observations can resolve this ambiguity. Radar systems bounce a radio signal off the asteroid and measure the return, providing direct information about the object's size, shape, rotation state, and surface roughness that is entirely independent of albedo. The Goldstone Solar System radar and the Arecibo Observatory, before its collapse in 2020, represented the primary radar characterization assets for near-Earth objects. Radar observations have produced extraordinarily detailed 3-dimensional models of asteroid shapes, revealed binary asteroid systems where a smaller moon orbits a larger primary, and refined orbital determinations to the precision required for accurate long-term impact probability calculations. But radar characterization requires the object to be within a limited distance range, the radar system to be available and pointed at the target, and sufficient lead time to plan and execute the observations. For objects discovered days before their closest approach, detailed radar characterization is often not feasible within the available window. The object passes before the observations can be completed. NASA's planetary defense programs have made substantial and genuine progress that deserves recognition before the gaps are emphasized. The DART mission, which deliberately impacted the moonlet Dimorphos orbiting the asteroid Didymos in September 2022, demonstrated something that had never been demonstrated before: that humanity possesses the technical capability to alter the orbit of a near-Earth object through kinetic impact. The mission changed Dimorphos's orbital period by approximately 33 minutes, significantly more than the minimum success threshold, validating the kinetic impactor concept as a viable planetary defense tool. The follow-up Hera mission from the European Space Agency is designed to characterize the impact site and the resulting orbital changes in detail, providing the scientific measurements needed to refine models of how kinetic impactors perform against different asteroid types and structures. These are not minor achievements. They represent the transition of planetary defense from a theoretical planning exercise to a demonstrated practical capability. The upcoming Niño Surveyor mission, a space-based infrared telescope specifically designed to search for near-Earth objects from a vantage point near the Sun-Earth L1 Lagrange point, is intended to dramatically improve detection completeness, particularly for objects in the difficult angular regions near the Sun that ground-based surveys cannot access effectively. By observing in the infrared, Niño Surveyor can detect the heat emitted by asteroids rather than relying solely on reflected sunlight, providing better size estimates alongside discovery and reducing the albedo ambiguity that plagues optical brightness measurements. The mission represents a targeted technological response to a known and characterized gap in the detection architecture. Its development and eventual deployment represent the planetary defense community doing exactly what it should be doing, identifying the limitations of current systems and building the next generation of tools to address them. But the gaps remain real in the present tense, before Niño Surveyor reaches orbit, and before its survey accumulates the years of data needed to achieve meaningful completeness improvements. Scientists estimate that a significant fraction of objects in the size range capable of causing regional destruction, roughly 100 to 300 meters in diameter, remain undetected in the current catalogue. Objects in this size range would not end civilization. They would not trigger a mass extinction. But a 100 to 300 meter impactor striking a populated region or generating a tsunami from an ocean impact could kill hundreds of thousands to millions of people and cause physical destruction across an area the size of a small country. The fact that a meaningful fraction of such objects remain uncatalogued is not a failure of the planetary defense community, which has achieved remarkable results with the funding and technical resources available to it. It is a statement about the scale of the observational challenge relative to the current level of investment in meeting it. The orbital geometry problem is worth understanding clearly. Objects on certain orbital paths spend a significant fraction of their time in the angular vicinity of the Sun as seen from Earth. Their orbits keep them interior to Earth's orbit, or on highly elliptical paths that bring them close to the Sun at perihelion and out to Earth-crossing distances at other points. From a ground-based perspective, these objects are preferentially visible near the Sun in the sky, precisely where ground-based optical surveys cannot look. They appear briefly in the observable sky during their approach, sometimes for only days or weeks before passing and receding. The combination of limited visibility windows and the sun-blocking problem means these objects are systematically underrepresented in detection surveys, regardless of how many nights of telescope time are devoted to the search. The story here is not one of imminent impact, predicted catastrophe, or negligent oversight. It is one of honest assessment of detection capability at a specific moment in the development of planetary defense as a scientific and technical discipline. The things we can see we watch carefully, model with increasing sophistication, and track to orbital precisions that would have seemed extraordinary to the astronomers who established the field. The things we cannot yet see represent a known unknown, a characterized gap in the map with understood causes and a development roadmap aimed at closing it. Progress is real. The gap is narrowing. The tools being built will, within the coming decade or two, dramatically improve our catalogue completeness for objects in the most dangerous currently under-characterized size ranges. But the gap has not closed yet, and the universe does not wait for our catalogues to be complete before sending visitors through the neighbourhood. Sometimes the most important scientific statement available is a simple, clear-eyed acknowledgement of what we do not yet know, paired with an honest account of what we are doing about it. Planetary defence sits in that position today, knowing enough to understand the shape of its ignorance and working steadily to replace that ignorance with knowledge. The question is whether the timeline of that work is well matched to the timeline of the threat. That is a question that deserves more public attention than it currently receives. Part 12. The Strange Behaviour of Interstellar Visitor. 3I. The first confirmed visitor from outside our solar system arrived in 2017, and the astronomical community nearly missed it entirely. Oumuamua, whose name derives from the Hawaiian term for a messenger or scout arriving from a great distance, was detected by the Pan-STARRS telescope survey in Hawaii on October 19th of that year, already on its way out of the inner solar system, already receding from the Sun after its closest approach. It had arrived, past perihelion, and was departing before anyone knew it existed. The detection window was narrow, the observation time was limited, and the object itself was unlike anything astronomers had encountered in the solar system before. In a field where discovery usually comes with the luxury of follow-up observation, repeated measurement, and gradually refined understanding, Oumuamua offered almost none of those luxuries. It was a one-time visitor moving fast, and the scientific community had to work with what little time remained before it vanished into interstellar space forever. What made Oumuamua unmistakably interstellar was its velocity and its trajectory. Objects gravitationally bound to our solar system, whether comets, asteroids, or planetary debris of any kind, travel on elliptical paths around the Sun. Their speeds are constrained by solar gravity in a way that produces characteristic orbital signatures, predictable relationships between distance from the Sun and velocity that have been understood since Kepler formulated his laws of planetary motion in the 17th century. Oumuamua violated those relationships. Its path was hyperbolic. It was moving too fast to be gravitationally bound to the Sun, arriving with excess velocity that solar gravity alone could not have imparted. When astronomers traced its trajectory backward through the solar system, the path did not originate from the Oort cloud, the Kuiper belt, or any known reservoir of solar system material. It came from interstellar space, from a direction broadly consistent with the constellation Lyra, possibly from the general vicinity of the star Vega, though the travel time at its observed velocity would have been so immense that Vega itself was not in that part of the sky when the object departed its origin point. It was, beyond any reasonable scientific doubt, not from here. It was the first physical object humanity had ever detected that originated from another star system, and we almost let it pass unnoticed. The shape inferred from its brightness variations was as puzzling as its origin. As Oumuamua tumbled through space, its brightness changed dramatically and periodically, varying by a factor of 10 or more as different faces rotated toward the Sun. The only geometric interpretation consistent with that degree of brightness variation was an object with an extreme aspect ratio, either highly elongated like a cigar several hundred meters long and only tens of meters wide, or extremely flat like a thin disc or pancake shape. Neither geometry has a clear parallel in the catalogue of solar system small bodies, which tend toward irregular but far less extreme shapes. Something about the environment in which Oumuamua formed, or the processes it experienced during its journey through interstellar space, had produced a geometry that our solar system apparently does not commonly generate. That alone would have been scientifically remarkable. But Oumuamua had one more anomaly to offer. As astronomers tracked its outbound trajectory with increasing precision, they detected a non-gravitational acceleration. Oumuamua was not following the path that gravity alone would predict. It was being pushed by something. In comets, this kind of deviation from a purely gravitational trajectory is well understood. Outgassing of volatiles from the nucleus, jets of gas escaping as sunlight heats the surface, produce a reaction force that nudges the comet off its gravitational path. The natural explanation for Oumuamua's non-gravitational acceleration was therefore outgassing, but extensive spectroscopic observations found no evidence of the gas emissions that outgassing should produce. No water vapour, no carbon monoxide, No cyanide or other molecular signatures that would betray the presence of sublimating ices. The acceleration was there. The expected cause was not detectable. This discrepancy generated a scientific debate that has not been fully resolved and produced one of the more memorable moments in recent astronomical history when a serious peer-reviewed paper by researchers at Harvard raised the possibility that the non-gravitational acceleration was at least mathematically consistent with the object being an artificial light sail of extraterrestrial origin. The light sail hypothesis is emphatically not the mainstream scientific position, which continues to favour explanations involving exotic outgassing mechanisms or unusual physical properties. But the fact that it was raised at all, by credentialed scientists in a legitimate journal, reflects how genuinely anomalous Oumuamua's properties were and how inadequate the available observational data was to definitively eliminate competing interpretations. The second confirmed interstellar object, Comet Borisov, arrived in 2019 and was, in almost every meaningful respect, a more cooperative and scientifically tractable subject of study. Amateur astronomer Gennady Borisov discovered it in August of 2019 while it was still months away from its closest approach to the Sun, providing the astronomical community with something it had almost entirely lacked with Oumuamua: preparation time. Telescope time across multiple facilities was allocated and coordinated. Spectroscopic observations were planned and executed at multiple points along the approach trajectory. And what those observations revealed was simultaneously reassuring in its familiarity and scientifically interesting in its details. Comet Borisov looked, in most respects, like a comet from our own solar system. It had a coma, the diffuse cloud of sublimating gas and entrained dust that surrounds an active comet's nucleus when solar heating begins vaporizing surface ices. It had a tail. Its spectroscopic signatures included water vapor, carbon monoxide, and other molecular species that are common and expected in solar system comets. The broad chemical similarity between Borisov and solar system comets carried a significant implication: the basic chemistry of planetary system formation, the fundamental mix of ices, organic molecules, and rocky material that goes into building small bodies around young stars, may be relatively universal across different stellar environments throughout the galaxy. Two star systems, separated by light years and formed from entirely different nebular material, had apparently produced objects with recognizably similar chemistry. That convergence tells us something about the universality of planetary system formation processes that no amount of remote observation of distant stellar systems could have revealed as directly. Borisov also showed differences that reminded scientists not to overgeneralize from chemical similarity. The ratio of carbon monoxide to water in Borisov's outgassing was higher than in most solar system comets, suggesting a formation environment that was either colder, more carbon monoxide rich, or both. Small differences in molecular ratios encode significant information about the temperature and chemical structure of the protoplanetary disk in which an object formed, the distance from its parent star where condensation occurred, and the radiation environment provided by the parent star and any nearby stellar neighbours during the critical period of planetesimal formation. Borisov was familiar enough to confirm that cometary chemistry is not entirely alien across stellar systems, and different enough to remind astronomers that each system leaves its own fingerprints. Now there are preliminary reports of a third interstellar candidate tentatively designated 3I, and the early measurements are generating precisely the kind of carefully contained excitement that characterizes a field that has learned, from Oumuamua's ambiguities, to be rigorous about what it claims before the data fully supports the claim. Spectroscopic observations suggest an unusually high methanol content compared to typical solar system comets. Methanol, a relatively simple organic molecule, is present in solar system comets but not usually at the ratios that preliminary measurements of 3I appear to suggest. The chemical signatures coming from this object appear to indicate a formation environment meaningfully different from the protoplanetary disk that surrounded our young sun 4.5 billion years ago. The significance of unusual methanol ratios requires some chemical context to appreciate fully. Methanol forms primarily through surface reactions on cold dust grains, in dense molecular clouds and protoplanetary disks, in regions cold enough for carbon monoxide to freeze onto grain surfaces and be processed by hydrogen atoms into methanol through a series of reaction steps. The abundance of methanol relative to water and other volatiles encodes information about the temperature history of the material, the radiation environment that processed the grain surfaces, and the specific conditions in the disk region where the object condensed. An object with anomalously high methanol ratios compared to solar system comets may have formed in a colder disk, around a cooler star, at a greater distance from its parent, or in a chemically distinct galactic environment, where the available raw material carried a different molecular heritage from previous generations of stellar processing. Each of these possibilities tells a different story about the star system from which 3I originated, and disentangling them requires more data than preliminary observations can provide. The interpretations of 3I's measurements are genuinely preliminary, and scientific caution here is not performative modesty. Early spectroscopic measurements of comets have a well-documented history of requiring significant revision as higher quality data arrives and as the object's behavior evolves with changing heliocentric distance. Outgassing rates and molecular ratios change as different volatile species begin sublimating at their characteristic temperatures during approach to the Sun. A composition that appears anomalous at large distances may look different when the object is closer and better characterized. The appropriate response to preliminary measurements of an unprecedented object is neither dismissal nor overclaiming, but careful continued observation and honest acknowledgement of what the current data can and cannot support. What is not preliminary, and what no additional data revision can diminish, is the broader implication of the pattern that Oumuamua, Borisov, and now 3I together represent. Interstellar objects are passing through our solar system, not occasionally as rare anomalies, but regularly as a feature of the solar system's environment in interstellar space. Current theoretical estimates suggest that the solar system may contain thousands of interstellar objects at any given time, the vast majority far too small and faint to detect with existing surveys. The detection of 3 candidates in less than a decade reflects improving survey capability rather than an actual increase in the rate of interstellar visitors. The Vera Rubin Observatory, designed to survey the entire visible sky every few nights with unprecedented depth, is expected to dramatically increase the detection rate when it reaches full operational capability, potentially delivering the first genuine statistical sample of interstellar objects whose properties can be systematically compared. In the coming decades, if a sufficiently slow-moving interstellar object arrives on a trajectory that provides adequate warning time and a geometrically feasible intercept path, a mission to fly alongside it and collect direct samples is no longer purely theoretical. The European Space Agency's Comet Interceptor mission is currently in development specifically to wait at the Sun-Earth L2 Lagrange point for a suitable target, whether a dynamically new comet or an interstellar visitor, and then fly out to meet it. It is humanity's first spacecraft designed with interstellar visitors explicitly in mind, a standing intercept mission waiting for the right traveller to come within reach. The thought that closes this section deserves to be held for longer than the pace of this story usually allows. Objects formed around another star, in a disk of gas and dust orbiting a sun we have never seen up close, processed by chemistry we're only beginning to characterize, ejected into interstellar space perhaps millions or billions of years ago, traveling through the cold dark between the stars for timescales that dwarf all of human history, and arriving in our solar neighborhood close enough for our telescopes to taste their chemistry and our spacecraft to potentially touch their surfaces. The universe is not as empty between the stars as it appears. It is full of travelers, and we are only just learning to see them. Part 13. AI discovers structures in space data humans missed. Modern astronomy is drowning in data, and that drowning is one of the greatest scientific opportunities in human history. The Gaia mission, the European Space Agency's project to map the positions and motions of over 1 billion stars in the Milky Way, has produced a dataset so vast that the entire history of astronomical observation before it is, in data volume terms, essentially a rounding error. The Vera Rubin Observatory, designed to survey the entire visible sky every few nights, will generate approximately 15 terabytes of data per night when it reaches full operational capacity. 15 terabytes every night for 10 years. No human team can examine 15 terabytes of astronomical images per night with the kind of attention required to find subtle, previously uncatalogued features. The mathematics of that task are simply prohibitive. A person examining one image per second would need roughly 4,000 years to look at a single night's worth of Rubin data. This is where machine learning systems have moved from useful tools to absolute necessities in modern astrophysics. AI-based detection algorithms have already demonstrated their value in concrete ways. Neural networks trained on known examples of gravitational lenses, regions where a massive foreground galaxy bends the light of a more distant background galaxy into distinctive arc shapes, have found hundreds of new lens candidates in survey data that human reviewers had classified as unremarkable. These lenses are scientifically valuable because they act as natural telescopes, allowing astronomers to study distant galaxies in far greater detail than would otherwise be possible. Machine learning systems scanning exoplanet transit data from missions like Kepler and TESS have identified planet candidates that were missed in initial human-led analyses. Some of these candidates, upon follow-up investigation, turned out to be real planets, adding to the census of worlds outside our solar system. The pattern recognition capabilities of trained neural networks can detect the subtle, periodic dimming of a star caused by an orbiting planet at signal-to-noise ratios below what human reviewers reliably detect. There is a philosophical dimension to this development worth sitting with. Science has historically been a human activity in a deep sense. Hypotheses form in human minds. Patterns are noticed by human visual systems. Intuitions about where to look next come from human experience and judgment. Machine learning systems are beginning to change that character. Patterns are being found in data that no human being ever consciously examined. Structures are being catalogued that were invisible, not because the data did not contain them, but because the data arrived faster than human attention could process it. Human astronomers still do the interpreting. They still design the surveys, train the algorithms, evaluate the candidates, and build the theoretical frameworks. The machine is not doing science autonomously, but the machine is finding things. And some of those things, when humans look at them carefully afterward, turn out to be genuinely new. The universe has been emitting information about itself in all directions for 13.8 billion years. We have been collecting a small fraction of it for a few centuries. We are now, for the first time, building tools capable of reading more of what it has been sending. Part 14. The magnetic pole is racing towards Siberia. Earth's north magnetic pole is not where most people think it is, and it has not been stationary for a very long time. The geographic North Pole, the axis around which the planet rotates, sits at 90 degrees north latitude. The magnetic North Pole, the point toward which compass needles point, has always been somewhere different, and it has always been moving. For most of the 20th century, it drifted slowly across the Canadian Arctic at a speed of roughly 10 to 15 kilometers per year. This was known, manageable, and relatively predictable. Then the pace changed. Beginning in the late 1990s and accelerating through the 2000s and 2010s, the magnetic North Pole began moving faster. By the time regular monitoring systems were capturing accurate positions, the pole was moving at speeds approaching 50 to 60 kilometers per year. Its direction had also shifted dramatically. Rather than continuing its slow drift across the Canadian Arctic, the pole began moving directly towards Siberia. It has continued on that trajectory. The practical consequences of this movement are not trivial. Aircraft navigation, maritime navigation, and every smartphone compass function relies on models of the magnetic field that must be regularly updated to remain accurate. The World Magnetic Model, maintained jointly by the United States National Geospatial Intelligence Agency and the British Geological Survey, is normally updated every 5 years. The accelerating motion of the pole forced an out-of-cycle emergency update in 2019 because the model had drifted outside acceptable accuracy tolerances for navigation systems. That is not a routine event. The geophysical explanation for the pole's acceleration points to changes in the flow patterns of liquid iron in Earth's outer core. The magnetic field is generated by that liquid iron convection, and changes in the convective patterns change the field geometry at the surface. Recent research has suggested that the acceleration may be linked to changes in a high-speed jet of liquid iron flowing beneath the Arctic region of the outer core, a feature that has been identified in seismic and magnetic field data. Whether that jet is itself changing as part of longer-term core dynamics remains an active area of research. A frequently asked question when this subject arises is whether the pole's movement signals an impending magnetic polarity reversal, an event where the north and south magnetic poles switch positions. The geological record shows that such reversals have occurred many times in Earth's history, most recently about 780,000 years ago. They are associated with extended periods of significantly reduced global field strength, during which charged particle radiation reaching the surface increases. These events have been studied in sediment cores and volcanic rocks, and they appear to have occurred gradually, over thousands of years rather than suddenly. Most geophysicists do not believe the current pole movement indicates an imminent reversal. The field has shown periods of rapid pole movement before without triggering a reversal. The field's strength, while showing regional weakening in areas like the South Atlantic anomaly, is not showing the global weakening pattern typically associated with pre-reversal conditions. But pole movement at the current rate and in the current direction is geologically unusual for the modern era. The field is dynamic. It is changing on human timescales in ways that have real navigation consequences and scientifically fascinating geophysical implications. The ground beneath our feet is not still. The core beneath that is even less so. Part 15. The real question. No one is asking. It is time to step back from the individual threads and look at what they form together. Over the course of this story, several systems have been described, each with its own scientific explanation, each grounded in measurements and data collected by satellites, ocean buoys, magnetometers, solar telescopes, and decades of accumulated scientific knowledge. None of these phenomena are fabrications. None of them are speculative in their basic existence. They are all real. A massive subsurface heat reservoir is building in the equatorial Pacific at a scale that has no documented precedent at this stage of ENSO development. Climate models that were projecting a moderate El Niño in January 2026 had escalated to strong or potentially super El Niño projections by March, a pace of forecast revision that is unusual and that is being watched very carefully by the scientific community. The global oceans have been running near record temperatures since 2023, providing the warmest possible background state for whatever the Pacific releases. Earth's magnetic field is showing structural changes of a complexity not previously recorded by satellite instruments, with the South Atlantic anomaly expanding and splitting into two lobes. The Sun has dramatically overperformed its forecast, producing a significantly more active cycle than predicted, and showing little sign of the quiet decline that was expected. The western United States shattered every winter temperature record on file, and then experienced 105-degree heat in March. Tornadoes, blizzards, a geomagnetic storm, and a record heat dome arrived in a single week, demonstrating an atmospheric energy state that forecasters find difficult to characterize in normal seasonal terms. Each of these has an explanation. The Pacific heat reservoir is a natural consequence of La Niña's collapse and the ocean dynamics of ENSO cycling. The solar cycle overperformance reflects the genuine difficulty of predicting solar magnetic activity from incomplete knowledge of the underlying processes. The magnetic field changes are driven by core dynamics that have been evolving for millions of years. The western heat and the atmospheric volatility reflect the combination of a changing Pacific, global ocean warmth, and a climate system that is carrying more energy than it carried a generation ago. The question that is not being asked loudly enough in public discourse is this: are we still in an era where these systems can be treated as separate, independent subjects for separate, independent specialists? Or are we entering a period where the interactions between these systems matter as much as the systems themselves? Earth is not a collection of unrelated phenomena sharing a planet by coincidence. It is a tightly coupled system of systems where the oceans talk to the atmosphere talks to the magnetic field interacts with the solar wind, and the solar wind responds to processes occurring 93 million miles away on a star. Models have always captured some of these interactions, but models are necessarily simplifications. They capture what we know how to parameterize. They cannot capture what we have not yet characterized. Modern instruments allow us to observe all of these systems simultaneously, with a precision that did not exist 30 years ago. This creates a possibility that did not previously exist, detecting coincidences at a scale that allows us to ask whether they are truly coincidences. The simultaneous anomalies described in this story might be exactly that, a statistical cluster, a run of independent bad luck across multiple systems occurring in the same few months. Complex systems are full of such apparent patterns that evaporate under rigorous statistical scrutiny. But the alternative possibility deserves honest consideration. The climate system may be entering a period of amplified variability, driven by the convergence of multiple drivers that are each, independently, pushing toward more extreme behavior. The Pacific is storing more heat than usual. The oceans backing it up are warmer than usual. The solar input is higher than predicted. The magnetic shielding has developed its most complex anomaly on record. If even a fraction of these systems interact in ways that amplify rather than average out, the behaviour of the climate system over the next several years could exceed anything we have used historical records to anticipate. The spring predictability barrier will pass. By early summer 2026, the Pacific's direction will be clearer. Scientists will have better data, models will have better skill, the range of outcomes will narrow, and the world will know whether the Pacific is delivering a once-in-a-generation climate event or whether the system has pulled back from the edge as it has before. But whatever the Pacific decides, the other systems are not waiting for its answer. The magnetic field will continue its complex evolution. The sun will continue producing events that no one fully predicted. The global ocean will continue accumulating heat with nowhere easy to put it. The atmosphere will continue behaving like a system that has been given more energy than it knows what to do with. The question that this moment in planetary history is quietly posing is not simply whether El Niño is coming. The question is whether the Earth system as a whole is entering a new mode of behaviour, one for which the last several thousand years of human civilization has not prepared us, and for which our observational record, barely a century and a half long, may not be sufficient to fully characterise. We built civilization in the climate we had. We are now, in real time, watching the climate that produced that civilization begin to do things it has not done within the human record. Whether that represents a temporary excursion or a genuine transition to a new regime, we cannot yet know with certainty. What we can know is this: the instruments are on, the data is coming in. The scientists are watching, and the Pacific Ocean, sitting on top of the largest subsurface heat reservoir ever observed at this stage of an ENSO cycle, is about to tell us something. We should probably be listening.